Hello and welcome to this AimHi Live, which is about electricity made easy. This one's about, it's mainly GCSE electricity, but that's basically, if you're not in the UK, that's basically like high school electricity. So today is about high school electricity. Thanks so much for coming, everyone who's showed up. Turns out it's a bank holiday. I did not know that. I'm so not on top of when the holidays are. But who's here? Miz here. Hi, mate. Right. Let's crack straight on. I'll just go straight into it. So yes, this one is called should we call it high school? I'm going to call it high school electricity because it's basically the same across all high schools. High school electricity. And for those, some of you will have been here on the last one when I was talking about. On the last one, we were talking about current, and I rushed through it a bit quickly actually. So now we're going to do the same thing but kind of slower, and with a bit of current, bit of voltage, and I think those are the two things we're going to cover. But first, what is this? What is this, everyone? What do you guys reckon these bricks are? What do people think? It's saying Minecraft. Okay, so these are not Minecraft, although they do kind of look like Minecraft. These are tiny little grains of these are tiny little grains of salt. Look how beautifully cubic they are. So when you're grinding up a delicious lump of salt, you're actually creating these tiny little grains, and they're cubic because that's how all the atoms stack. So for those of you who've done this bit of chemistry, you'll know that it's sodium plus and Cl minus, and they go in perfect squares with one another over and over again, repeating throughout the structure. And so they make perfect cubes. Yeah, theoretically you could make a salt cube that would be a perfect cube with every single sodium chloride lined up perfectly, one after the other. That would be like as big as a house. You just have to grow it really slowly and really carefully. Anyway, right, so yes, this one is called High School Electricity Made Easy, and we are going to talk about, well, first I thought what we'd do is do a quick check of current from last time. So let's go down here. Let's go down to the bottom. Right, what we'll do is we're going to create a circuit. So firstly, does anyone remember what this symbol stands for? What does this symbol stand for? What is this symbol here? Who remembers? Okay, so yeah, Ant's coming in as a battery, and it is a battery. A lot of places, and Jemima's saying battery as well, great. Now, a lot of places, annoyingly, if you're doing this at school, will make you call this a cell, so I'm just going to label it as a cell as well. But I'm happy for now for you to call it a battery. Anyway, right, so if let's put another component in there. Who remembers what this component is here? What is that one? So Miz saying bulb. Yeah, exactly. This is a bulb. So this bulb is going to light up because of this battery. So Jemima's saying a switch. So I'll show you what a switch looks like. A switch would look like this. Pop it in up here. The switch looks like that, and normally you show a switch as being open. So you've got a dot on either side, and you can see that you could swing that bit of wire closed, and you could close the switch. Now, which side of the battery is positive and which side is negative? So who thinks the left is positive and who thinks the right is positive? Which side of the battery is positive? Votes coming in. What do you guys reckon? Which side of the battery is the positive side of the battery? Okay, so Zukil is guessing right. Miz is saying left. Okay, so the left side of the battery is positive and the right side is negative. Now, the way that I remember this is if you take this side here and you break it into two pieces, then you've got one piece and another piece, and you can flip that other piece around to make a plus, whereas this side here is only really small, so you can only make a minus sign with it. This is only big enough to make a minus sign, whereas this you can break in half to make a plus. So that's how I always remember that's plus. Right, okay, next thing. Now, electricity is the flow of something. What is electricity the flow of? There's something flowing around the circuit. What is it? It's a tiny, tiny particle that's flowing around the circuit. Electrons, great. So electricity is the flow of electrons. I'm just going to quickly write that down. Flow of electrons. Now, which way do the electrons flow? Do they flow clockwise or anti-clockwise? Maggie and Nidex fun. It's finally late. Today we're learning about high school electricity made easy, mate. Right at the top. We're just at the moment we're just getting into it, so I'm just asking some questions about how to make a circuit. So this, people have said, is a bulb, this is a battery, and this is a switch. The left side of the battery is positive, the right side is negative, and electricity is the flow of electrons. The question is, which way around the circuit do the electrons flow? Clockwise or anti-clockwise? Okay, Nilex is saying anti, it's Maggie saying anti, Sukil is saying anti, Miz is saying clockwise. Miz is the only one who's correct. And Val's watching this to do homework as well. Miz is the only one that's correct. The electrons are flowing clockwise. The electrons are going this way around the circuit. Because electrons have a negative charge. You often write them as E minus. Electrons have a negative charge. And if you have something negatively charged here, then it will be attracted towards the positive side of the battery. And if you have something negatively charged here, then it will be repelled away from the negative side of the battery. So the electrons flow from negative to positive. Right, now, I told you this last time, but there's something weird about this, and it's to do with how we discovered electricity. So when we discovered electricity, it was like we didn't understand how it worked. And so when we talk about current, in school or at university or whenever, if you're looking at electricity, which way does the current flow around this circuit here? Clockwise or anti-clockwise? So Maggie's right this time. Yeah, Maggie's saying it's going anti-clockwise. So the current goes anti-clockwise from positive to negative. Now, this is bizarre and actually really annoying, and it's one of the things that I kind of struggled with for a little bit, because we know that the electrons are going from negative to positive, and that's what electricity actually is. But whenever we do anything to do with electricity, you have to think of it as going from positive to negative, the other way around. All of the rules that were ever made about, sorry, not all the rules that were ever made, but loads of the rules that were made about electricity were made before anyone actually understood what electricity was. And so all the rules are based on electricity going from positive to negative. So whenever we talk about current, you have to think about it going from positive to negative, which is kind of easy to remember in some ways because positive sounds like it's producing something. So we think of the current now as going anti-clockwise around here. Right, okay, cool. How do we measure current? What units do we use? Maggie wants gold star. Yeah, Maggie, you can have a gold star, of course. You got the flow of current right. That's all you need. Okay, Jemima's saying amps. Great. So amps is how you measure current, and what do you use in order to measure the current? So we're going to measure it in amps, but we need some kind of component to measure it with. Does anyone remember what that is? And while I'm waiting for that to come in, here's a picture of David Attenborough with a huge egg and a side quest that you can go on if you're not interested in telling me about. I mean, I'm going to go back to the circuit in just a second, but does anyone know what this egg is for? What kind of egg is this? And why is Attenborough holding it? Anyway, think upon that, if you will. And now I'm just going to go back to this circuit. So has anyone said the right answer about how... Nilex is saying they skipped the last class. That's all right, Nilex, because I'm kind of actually reviewing a lot of the same stuff that we did last time, so it's all good. So the component that you use to measure electricity is called an ammeter. I'm just going to write that out. Ammeter. Or RE the other way around, depending on if it's American or English. Anyway, so yeah, an ammeter is used to measure the current in a circuit. Now, the best way to think about an ammeter, I think, is like a windmill or like a water mill. And so if you imagine like a river flowing past like this, and it's flowing in this direction, then to measure the speed of the river, all you need to do is dip a little water mill kind of propeller inside it, and the water mill will tell you how fast the river is flowing, right? By how quickly it spins around. And an ammeter is the same thing. It just sits in the circuit, in the stream of the current, and it spins to tell you how quickly the current is flowing. And someone else already correctly said that this is measured in amps. So amps tells you how much the current is flowing. And it's really, I find it much easier with current to think about it as like water. Think of it as this watery kind of thing that's flowing around the circuit. Right, just a really quick welcome to anyone who arrived late. Thanks for coming. This is an AimHi Live. We're doing most of these on like big questions like, is water wet? Should trees be paid the same as footballers? That kind of stuff. But every now and then we're running these ones that are on the syllabus stuff to help out on like more specific things. So that's what this one is today. If you want to come to ones that are on bigger questions, check out the calendar that is on this website. Like yesterday, I did a big one that had quite a few hundreds of people on it, actually, that was called Should Schools Ban Beef? And those are the kind of conversations we're having on the other ones. And this one is very much focused on electricity and going over the basics of how it works, because I feel like electricity is taught really badly in a lot of schools. It's taught well in some, but like a lot of schools teach it really badly. So I'm going to try and make it really simple. Okay, so Alan's on this one. Oh, great. Okay, so, and also another thing is if you're watching on Facebook, you won't be able to see most of the messages coming in. You're only able to see most of the chat by being on this one. Okay, so current is the flow of electrons. So just one more time to ask again, which way does the current flow around this circuit? Maggie's guessing up. Maggie, current can't flow up. The current is flowing clockwise or anti-clockwise? Yeah, so the current is flowing anti-clockwise from positive to negative, so round in this direction. Right, okay, so if you have a current of, let's say, 5 amps here, so let's say this measures 5 on this ammeter. If you then put another ammeter here, then what will the reading be on that ammeter? What do you guys think? And the dollar ball has come in to say, is it an ostrich egg that David Attenborough is holding? It's not an ostrich egg. It is a different kind of egg. Keep thinking on it. Okay, so answer's coming in 5. Brilliant. Yeah, so Nidex has got it right. Casey's got it right. Vendi Blessugar. Vendible Sugar. And 100T. Yeah, great. Okay, so it's 5 amps will be here because the other thing that you should remember about current is it's like a back-to-back traffic jam. So you have to imagine that all the electrons are absolutely rammed next to one another. In fact, it was my... I feel like I have a memory of it being, it's someone in my family, and I feel like it was my uncle who was talking about how in France cars like drive right one after the other, and it's obviously not the case everywhere, but if you can imagine a traffic jam where everyone is nose to tail and completely backed up behind one another, then each car can only move if the car behind it moves, if the car in front of it moves as well, and the car behind can only move if the next car moves. And so every single car in the traffic jam has to move at exactly the same time for any of the cars to move. And that's what current is like. And so if you have 5 amps flowing here, then you must have the same current over here because it's a back-to-back traffic jam all the way around. Right, okay, now let's see who remembers. Let's just go above David. Let's go up here, Mo. Okay, so if we have a new circuit like this, again, I'm putting the positive on the left, the positive to the long side, and the negative to the short side. Let's say now we have an ammeter here, and let's have another ammeter here, and a bulb, and let's have another bulb here, and another ammeter here. Right, okay, so if the current on, in fact, let's break it up and put another ammeter in here. There's loads of ammeters. If the current in the first ammeter is 6 amps, then what will the current be in this one, and this one? So this is answer number 1, this is answer number 2, and this is answer number 3. What do you guys reckon? Oh, Lou's coming with exactly the right answer. And Maggie's saying as well, it's an elephant bird. Maggie, you could have hundreds of gold stars for that. It's a great elephant bird guess. Okay, Nilix is saying all 6 amps. Mears is saying 3 amps, 3 amps, and 6 amps. Okay, right, so lots of people are not sure what's going on. Right, so let me explain what happens. So, the current, as we know, we're pretending it flows out of the positive side. We know that current actually goes out the negative side, but when you talk about electricity, you always talk about it coming out the positive side, even though it's wrong, but that's madness. Anyway, so the current is flowing along, and it flows along this line here, this wire, until it gets to the first ammeter. And so the first ammeter, it flows through and it shows that it's flowing at 6 amps. So that's the rate of flow. Now, when the current gets to here, it has a choice, and it can choose, do I go this way or do I go this way? Now, which route do you reckon is harder to go down? Which route is harder to go down, this route or this route? And Miz saying they're the same, and the answer is they are the same. So when you're looking at electricity, you ignore the length of wires and you pretend that length is irrelevant. All that matters is what it's got to go through. So the current considers this way, and it's like, well, I have to go through a bulb and an ammeter. And it looks this way, and it has to go through a bulb and an ammeter. So actually, both routes are just as hard as one another. And so rather than the so the current will just perfectly split, and so you'll get 3 amps going this way, and 3 amps going this way. And so the current will run through the bulb, light up the bulb, and then will run through the ammeter, which will show a reading of 3 amps, and this one will show 3 as well. And then when they come together again, what will you get in this final ammeter? What will be the reading there? What do you guys think? So Bromley's saying the second one is longer and has more resistance. So Bromley, you're right that there would be a tiny, tiny amount more resistance from the extra length. But when you're drawing circuits, you always ignore the extra length, and you consider it not relevant, because otherwise it becomes hard to draw the diagrams and making sure you've got all the lengths the same. Okay, exactly. So they come together and make it makes 6 amps again. Perfect. Right. Okay, let's try another one. Okay, let's draw this on David Attenborough's elephant bird egg. Is red going to show up? Yeah, I reckon so. Okay, so now let's have another ammeter there. And let's have bulb. And in fact, I'm going to stop drawing the ammeters now, and I'll just point to the bit of the circuit where I want you to tell me what the current is. So all of these bulbs are the same. So they're all the same bulb. Now, firstly, which way does the current flow out of the battery? Does it flow to the right or does it flow to the left? What do you guys think? So we've got a few people saying left and a few people saying right. So yeah, the electrons go left, but the current, we say, goes to the right. Someone's asking if we teach classes outside of this. Yeah, so AimHi, if you check out the website, www.aimhi.co, is running loads of lives all the time during the lockdown. Here are the ones that are coming up next week, or some of them. I'm doing Is Water Wet? Is James and the Giant Peach propaganda? That's English. Am I the same person I was yesterday? Philosophy. Should we be paying trees more than footballers? These are some of the ones coming up next week. This one is like on syllabus, because I want to do some where I'm just like helping with the exact syllabus that people are doing at school. So this is electricity at school, made easy. Okay, so answers were coming in and people were saying, yeah, that the electrons flow to the left, but we talk about the current flowing to the right. And I'm going to start using the symbol for current, which annoyingly is I, and I know that's so irritating, but it's because C is used up for another thing in physics called capacitance, and then the next in line for it was charge, and they've given that a Q. And so annoyingly current is going to be an I, and you're just going to have to find a way to remember that. I don't know, for some reason that stuck in my head, so I never needed a special way to remember that. But somehow you need to remember that I is current. Current's going this way. So if this ammeter reads, let's say 12 amps, then my question to you is, what will an ammeter read if you place it at position 1, at position 2, and at position 3? And if you can only answer one of those, then just say the answer that you know. But let me know what you think the current will be at position 1, position 2, and position 3. Uh-oh, says it's Maggie. Yeah, it's hard. Okay, so Nidex wants me to go over waves and Lewis structures. Yeah, I can go with that, but not in this one because this one's going to be about electricity. But I can do that sometime for sure. Casey is saying 3, 6, and 12. Okay, so one of yours is right, Casey. Vendible sugar, yours is great. Right, let's talk about why this works. So 12 amps arrives here, and the current gets to this junction. And it has to decide, do I go this way or do I go this way? Which way is easier? Route 1 or route 2? Which is easier for the current to go down? This way. Yeah, Maggie, you're right, it is. That way. Maggie and Nidex, you guys are friends, aren't you? So it doesn't go route 1, it goes route 2. Route 2 is easier because it only has to go through one single bulb, whereas route 1 it has to go through 2 bulbs. So this way is doubly as hard as this way. So the current splits up with 4 amps this way and 8 amps this way. 4 this way and 8 amps this way, because this way is doubly as easy, this is doubly as hard. And because this is doubly as easy to get through, because it's only got one bulb on it, it has double the current going this way. Doubly. And then when they come back together, you get 8 amps here and 4 amps here, and they combine to give you, again, 12 amps at the end. So it comes out as 12 amps, and then 12 amps continues to flow through the battery, and then back out the other side. Right? Right. Doubly cool. Okay, I'm going to do one more on current, and then I'm going to switch over to voltage. So this time, this is going to be a bit harder on current. So if you're feeling that as I go through these, you're finding each one is like harder than the last, and you're thinking, why can I not get any of these? That's because each one is harder than the last, and I'm just teaching you the concepts. And you'll find if you get each one as I do them, then you'll find when you go back and do this, it'll be a lot easier than you thought before. So. Right, let's have another circuit here. Now, this circuit, instead of having bulbs on it, has got resistors. Now, resistance is measured in something called ohms. Now, so this is going to be a 1 ohm resistor. And this is going to be a 3 ohm resistor. Now, a resistor is just a thing on the electric circuit that makes it hard for electricity to flow through it. So don't worry too much about what it is yet. I'll come back to that in another thing. This is, I just want you to think about the current, which again is going to flow out of the positive, or we pretend it does, and it's going to get to here. Now, at this point here, if we put an ammeter here, then your current reading is 8 amps. So the question is, what will the current reading be here? So position 1, here, position 2, and let's do here position 3 and here position 4. What do you guys reckon all of those currents will be? Go. And while you think about it, I'll just be quiet. Actually, I'll just read the chat. Drift's asking what they are watching. Drift, you're watching a lesson about high school electricity made easy, mate. In fact, Drift, I'm interested. Are you watching on my YouTube, as in like Matthew Shribman's Science the Bath? Because if so, then this is a very syllabus-focused lesson for high school about physics that I'm doing, and you can get involved if you want. Yeah, but Drift, all the viewers are on Twitch. Right. Okay. So 1, 2, 2, 6, 3. Okay. Cool. So number 1 is gonna be 6, 2, 2, 8. Yeah, Vendible Sugar's got it as well. 6, 2, 2, and 8. Nidex has got it too. Great. So yeah, we'll have 6 amps here, 2 amps here, 2 amps here as well, because it's just the same bit of circuit. And then at the end, you'll have 8 amps. So to explain that, the 8 amps gets to here and it looks at the 2 roots, and it's like this is 3 times as hard as this route. So therefore 3 times as much current goes this way, because this is 3 times as easy. So 6 is 3 times 2. And that's how it works. Cool. So that's the end of current. Now let's talk about voltage. So voltage is a kind of different thing that is best to think about as if it's money. Rather than thinking of current as being like the flow of electricity down the circuit, voltage is better thought of as like money. So if you have, I'm going to use resistors again. So first we're going to start with two resistors that are the same. So let's have a 3 ohm resistor and another 3 ohm resistor. So they're both just as resistive as one another. They're the same resistors. Okay, so let's say this battery is let's say it's an 8 volt battery. Now, voltage is kind of thought of as, well, I was telling you to think about it as like money, as like spending money. It's kind of like the energy that the battery gives to the electrons as they're flowing around the circuit. And so even though it's called voltage, for now I want you to think of it as energy. It's like this energy that's being pushed around the circuit. Now, the current leaves the battery and it's carrying with it 8 volts. And as it goes around the circuit, it arrives at the first resistor. Now, what the aim of the voltage is always to spend all of itself before it gets back to the battery, but to spend it in the way that's most effective for getting through the obstacles ahead. So here, both of the obstacles are equally hard to get through. So it needs to spend, how much do you think on each one to get through both of them? So Miz is saying 4, exactly. So you spend 4 volts to go through each component. So 4 volts on the first one, 4 volts on the next one, and then it's out of voltage, and then when you get back to the beginning, you pick up more voltage and go around again. Cool, okay, right, now let's try where you have, let's try an 8 volt battery, but now let's drop this voltage down so that it is only 1 ohm. Sorry, let's drop this resistance down so it's just 1 ohm. So now this is just 1 ohm. So the 8 volts again comes along and it wants to spend a bit of itself here and a bit of itself here. What do you think it spends on each resistor? How much will it spend on the first resistor and how much will it spend on the second resistor? So exactly, everyone's saying 6 and 2 and Linux was first. There was lag. Lies! There's no lag right now. Maybe there was. Anyway, you're exactly right. Yeah, 6 volts on the first one and then 2 volts on the second one, because this one needs more voltage because it's harder to get through. So voltage spends itself where it's needed. Right, okay, let's try and tie this all together into... I'm not going to show you how voltmeters work this time. I'll do that next time. So let's tie this all together into this last problem that I'll do for you guys. So if you have a 12 volt battery, and then you have this circuit here. So let's make this, that could be 2 ohms. I'm not going to write ohms, I'm just going to write that the resistance is 2, so it's clearer. That can be 2, this can be 1, and this can be 4. So first question is this: what is the voltage going to be at this resistor here? And I know I haven't quite covered this yet, but what do you guys think the voltage will be at that resistor? Oh, Posy Joe got it right. Brilliant. I'm so glad you're getting it right. Well, I hope that I'm explaining it in a way that it's clear. Okay, so Venerable Sugar's saying 12. Anyone else got any thoughts on what the voltage will be at that resistor? Casey's saying 12 as well. Yeah, exactly. It's going to be 12 because the voltage, if you imagine the voltage as being the spending money that the current has, then it leaves from here and it gets to this point here. And then if it goes this way, it can afford to spend all 12 on this before it then returns back to the battery. So it only has to go through one obstacle. It can spend 12 volts on here and then return back to the battery to pick up another 12 volts. Whereas if it goes this way, then what will be the voltage over this one? So number 1, and what will be the voltage over this one, number 2? And oh, actually, I'm really sorry. I meant to write that as a 3. I'm going to change that to a 3 because it'll be easier. Put in the wrong number there. This is going to be 3 instead. What will the what will the voltage be over number 1? What will the voltage be over number 2? minus 10 brain cells. Brain cells are running out. This is the last question that I'm giving to you guys, and then we are off. So yeah, brilliant. It's Maggie's come in with exactly the right answer. So there will be 3 volts over the first one and 9 volts over the next one, because the voltage has got 12 to spend. It arrives at the first one. It can only afford to spend 3, so that it can afford to spend 9 here, because this is 1 and this is 3. So you need 3 times as much voltage to get through this resistor. Perfect. Okay, great. Right, now, if I tell you that... Okay, so if I tell you that the current here is 9 amps, then what do you guys think the current will be at position 1 and at position 2? What will the current be at position 1? What will the current be at position 2? So Mears is saying, will voltage only choose one way and not have to split like the current? So whilst I'm waiting for answers 1 and 2, current is like this flow of electrons flowing around the circuit, and as they flow in a river, the river has to flow in one direction or the other. And so some of the current flows this way and some of the current flows that way, and that's why it splits apart. However, voltage you can think of as the amount of money being carried by each single electron. So each electron is carrying a little pocket full of money, which we think of as that voltage spending money. And each single electron is only going to go in one direction. So if it goes this way, then it has all 12 volts to spend on that before it can then return. Whereas if it goes this way, then it's got to spread that 12 volts over here and here. So you end up with 12 volts down each line of the circuit, and you might have heard these in school being called parallel. These 2 bits are in parallel with one another because the electricity can choose to go down one way or the other way. And so when they're in parallel, you get the same voltage on each line. And the next saying, can I go to the bathroom? Yeah, of course, do whatever you want. Is there... Okay, so Nilex is saying 1, 9, and 2 is 9. So this is now going back to amps. So amps is the current. So with the current, you have to think the current does split. So the current of 9 amps is going to arrive, well, let's say it's coming out the positive side of the battery. The 9 amps of current is going to arrive at the junction, and now it has to decide which way is it going to go. Which way do you think it makes sense for it to go? So Casey is saying maybe 6 amps goes this way, and maybe 3 amps goes this way. Now, why would that be the case? Why would you get 6 amps going this way and 3 amps going this way? And Nidex is saying the other way around, saying maybe 3 amps go this way and 6 amps go this way. Posey J keeps getting spoiler alerts for the answer. Yeah, everyone gets spoiler alerts because the chat comes in sooner. You have to ignore the chat for a bit if you want to not get spoilers. And Nidex has switched their answers 6 amps and 3 amps. Right, exactly. So you'll get 6 amps going this way because the total resistance down this line is 2, and the total resistance down this line is 4. So this direction here is doubly as hard to go through as this direction for the current, and so double the current goes this way, and so you get 6 amps this way and 3 amps this way. So, really quick wrap up of what that is. Let's go over to this battering ram. I'm just going to ignore that. So, really quick wrap up of what we covered today is this. Current always goes from positive to negative, although we know that the actual electrons are going the other way around. Even though that's bizarre, that's the way the rule is. Current will split and take the easiest path. Current will take the path of least resistance. And so if the current sees that it can take an easier path through the circuit, i.e. only going through 1 resistor instead of going through 2, then more current will flow this way. So if this way is doubly as easy, then double the current will go this way as goes this way. That's how current splits. But if you're just in a single circuit with no options about ways to go, then the current will be the same the whole way around the circuit because it only has one place that it can go. That's current. Current is symbolized with an I, which is bizarre, and for some reason you just have to remember that, and it's measured in amps. Voltage is doubly. Voltage is always written on the battery, and the voltage, let's say it's something like 9 volts. Voltage is like spending money, and the voltage is attached to the charges as they go around the circuit, and so you get 9 volts. Everything carries 9 volts this way, and everything carries 9 volts this way as well. And then the 9 volts is split evenly over the challenges ahead. So this resistor here will get a full 9 volts, because once it's spent, all the charge carriers can then head back to the battery to get their spending money again. Whereas going this way, you will get only 4.5 volts over each of these. Or it will split going to where it's needed. So the voltage goes to where it's needed. So if this resistor was 1 ohm and this was 2 ohms, then the voltage would split, so you get 3 volts here and 6 volts here, because it goes to where it's needed, and then it's spent all of its 9 volts, goes back to the battery, and the whole thing starts again. Right, okay, thanks so much for coming, everyone. This has been an AimHi Live. Actually, a few of you are here for the first time, this is a bizarre one to come to first, but by all means, welcome. Thanks for coming. Most of them are on these kinds of topics, which I've just thrown up here, so do come back next week if you want to see them. And Nidex is asking a question. I'm about to answer questions in a sec, but I just wanted to say, for those who it was the first time, if you go to this website, then you can sign up for the calendar of what's coming up, and you can follow the Instagram as well, which is AimHi Live, if you want to see what's coming up each day. If you have any feedback for us on how we can make it better, that would be so good, because we're basically like a group of people who are doing this voluntarily to make a good thing during the lockdown, to kind of entertain, but also like explain some cool things. And if you want to help us if you want to give us some feedback, then please do. That would be great. And yes, Maggie, there will be so many gold stars available for doing that. I'm gonna answer the questions in just a second. I just want to send you all the link to giving feedback in case you are able to, because that would be so appreciated if you can. It is, if you're on the website. If you're on the website, then you should be able to just give feedback straight underneath the stream. So straight underneath the stream, you'll find an option to give feedback, and please do. I will just send the link there anyway, so that everyone has it. Right, okay, questions. Going back to what people were asking me. So someone said, okay, wait, how do the electrons stay grouped up together? That's going into like the chemistry of how the particles actually work. So it's more that like the electrons are all in a metal. There are loads of like metal centers that are surrounded by electrons, and so if these are the metal centers in like a piece of metal, if you zoom in really, really close, then they're surrounded by this kind of sea of electrons, which is what flows when we have electricity, and the sea of electrons will just like flow through the orange kind of metal centers that stay in the same place. But the reason they all stay together and they're in this back-to-back traffic jam is that every metal center needs to always own the same amount of electrons, otherwise it becomes unstable and the whole thing starts to destabilize. Mears is saying what attracts the electrons back to the negative side. So just to go back to that, there is no... so the electrons actually come out of the negative side. So even though we say that current goes this way, from positive to negative, in reality, the electrons flow the other way, and they're attracted to the positive side and repelled from the negative side. And I think that was all the questions that people asked. So thanks so much for coming. Someone, Bromley gave a great answer back there. I didn't say it was good. Anyway, it was good. Anyway, thanks so much for coming. I will see you guys next week if you're going to come to any of these. Farewell. Bye-bye. Maggie, enjoy the star. Maggie, yeah, you're worth all the stars. Have as many as you like. Farewell.